Rayleigh proposed damping which includes both C is going to be A 0 m plus A 1 k. Therefore, it is a combination of mass and stiffness proportional in that case damping ratio at nth mode is given by the damping ratio for stiffness proportional is equation 6, damping ratio for mass proportional is equation 3. Therefore, damping proportional for a combination of this could be simply the addition of this, that is A 0 by 2 1 by omega n, because for mass proportional damping is inversely proportional to omega, plus A 1 by 2 omega n, because for stiffness proportional damping ratio is directly proportional to omega n. I call this equation number 8. Of course, this is my equation number 7 given by Rayleigh. So, therefore, once we said zeta n is actually A 0 by 2 1 by omega n plus A 1 by 2 omega n, the coefficients A 0 and A 1 can be determined for a specific damping ratio zeta I and zeta j respectively for ith and jth modes. So, now the damping will look like the plot as shown now. The original damping, which is mass proportional, is omega n and this is zeta n. The mass proportional damping looks inversely proportional to omega increase. This is, I should say, C is equal to A 0 m, whereas the stiffness proportional damping is directly proportional to omega n. So, I should say in this case C is A 1 k. Rayleigh gave a combination of these two. It says that let it be a combination of mass proportional and stiffness proportional. This is Rayleigh damping. So, for any specific value of omega I and omega j, this is omega I, this is omega j, I should be able to get the same zeta. So, pick up zeta in such a manner that it is same for omega I and omega j as shown in the figure. So, zeta I is going to be A 0 by 2 1 by omega I and zeta j is A 1 by 2 omega j. Hence, zeta n is A 0 by 2 1 by omega n plus A 1 by 2 omega n. So, I can now say zeta I zeta j is actually equal to half of, I am expressing this in a matrix form, I am expressing this relationship in a matrix form 1 by omega I 1 by omega j of A0 A1. One can read this equation and similarly understand zeta I is equal to A0 by 2 into 1 by omega I plus A1 by 2 omega I, which is as same as this. So, now for zeta I, zeta j is same as zeta, then I call this matrix as A matrix. Let us work out A inverse. It is very simple to find out that it is going to be twice of omega j by omega I minus omega I by omega j of omega j minus omega I minus 1 by omega j 1 by omega I. I can easily find A0 A1, which are the coefficients of the damping matrix, as twice of omega I omega j by omega j square minus omega I square of omega j minus omega I minus 1 by omega j 1 by omega I of zeta 1 and zeta 2. We now say zeta 1, zeta 2 are same zeta, that is a condition. You see here omega 1 zeta 1, omega 2 zeta 2, they should be same zeta. For this condition to be implied, I can now say A0 is going to be twice of omega I omega j into omega j minus omega I of zeta divided by omega j square minus omega I square. I am just finding out this value. A0 is twice of this zeta 1, this zeta 2. There is no zeta 1, zeta 2, there are zeta divided by this, that is what I am writing, omega I omega j omega I zeta minus omega zeta. You can see that is what I am writing, and so on, which can be simplified as 2 zeta of omega I omega j by omega I plus omega j, because this can be, the denominator can be expanded as a square minus b square. I get the product, I can cancel this, I will get this value. Okay. That is my A0, equation number 10. Similarly, reading from the second row of this equation, A1 will be equal to twice of omega I omega j by omega j square minus omega I square of 1 by omega I minus 1 by omega j, because this omega j is minus is negative, okay, j of zeta, which says 2 zeta omega I omega j into omega j minus omega I by omega j of omega j square minus omega e square. So, this goes away, I can now say it is going to be 2 zeta 1 by omega j plus omega I get A1, equation 11. Now, C is actually equal to A0 m plus A1 k, which is given by Rayleigh. So, for the known values of A0 and A1, one can find C matrix, because m and k are already known. There are some observations on this condition. Some observations are: In applying this procedure of Rayleigh damping, the modes I and j with specified damping ratio should be chosen. The condition is, in the chosen modes for different frequencies, same damping ratio is applied. So, you should be able to choose two different frequencies which has the same damping ratio. Okay. Further, in order to check, examine damping in other modes, for the same ratio. For example, if it is a 3-degree freedom system model, three modes need to be included in the analysis. Then the damping ratio in all the three modes should be roughly same. I should say the word roughly same, because you cannot get exactly the same ratio which is desired to apply this method. Okay. Let us take an example problem which we already solved. The example problem is let us say this is M1, M2 and M3, this is K1, K2 and K3. Let M1 and M2 and M3 be a constant value which is 3500 kg, K1, K2 and K3 be a constant value, not constant, let us take it like this. K2 is 1.5 K1 and K3 is 2 K1 and K1 is K, which is 1500 kilonewton per meter. Okay, let us say this data is given. So, now the mass matrix and K matrix are known to us, which is required. I can apply any standard procedure what we discussed in the last lectures and find out omegas. Let us say I determine omega by influence coefficient method and the values are omega 1 is 0.57 root k by m, which is 0.57 root of 1500 kilonewton divided by 3500, let us say 11.8 radians per second, and the corresponding phi 1 is 1.68 and 0.32. Similarly, omega 2 is 1.414 root k by m. So, by substituting we get 29.27 radians per second, and the corresponding phi 2 is 1, -1 and -1. Similarly, omega 3 is 2.163 root k by m, which equals to 44.778 radians per second, and the corresponding phi 3 is 1 minus 3.68 and 4.68. So, the mass matrix is now known to me, which is m times of 1 0 0 0 1 0 0 0 1. From the equation of motion by force, Newton's force method, I can also find the k matrix. I leave this as an homework to you. K will be actually equal to 1 minus 1 0 minus 1 2.5 minus 1.5 and 0 minus 1.5 and 3.5. That is my k matrix now. So, M matrix can also be said as 3500, so much 1 0 0 0 1 0 0 0 1 in kg, and k matrix can be now said as 1500 into 10 power 3 of 1 minus 1 0 minus 1 2.5 minus 1.5 0 minus 1.5 3.5. So, now let us quickly compute A 0, which is 2 omega 1 omega 2. I am taking first two modes and I am assuming zeta to be 5%, okay, 0.05 divided by omega 1 plus omega 2. That is the equation for, you can see here for A 0, which is 2 zeta omega 1 omega 2 and sum of this, and A 1 is 2 zeta by this sum. Okay. Let us do that here. Which is going to be 2 into 11.8 into 29.27 into 0.05 divided by 11.8 plus 29.27, which gives me as 0.841. Similarly, A 1 is 2 zeta by omega 1 plus omega 2, 2.05, 11.8 plus 29.27, which is 0.0024. So, now I can find the C matrix as A 0 m plus A 1 k. So, that is C is going to be 0.841 into 3500 of 1 0 0 0 1 0 0 0 1, that is my mass matrix, plus 0.0024, that is my A 1 into 1500 into 10 power 3. Summing them up, we get C matrix as 6543.5 minus 36000 minus 36000 11943.5 minus 5400 minus 5400 15543.5 in so many Newton second per meter, because K matrix is in Newton per meter, mass matrix is in kg, C matrix is this. Now, I want to check what is my zeta 3, that is checking for the third mode. Zeta 3 I want to check. So, we know zeta n is A 0 by 2 1 by omega n plus A 1 by 2 omega n. So, zeta 3 is A 0 by 2 omega 3 plus A 1 by 2 omega 3. A 0 we know is 841 by 2 by 44.778 plus A 1 is 0.0024 and omega 3 is 44.778. When I estimate this, I get this as 6.31%, which is very close to 5%. Hence, we can say all three modes contribute to the response. So, Rayleigh damping is very easy to apply in a problem. We will take the numerical example of this through a computer code. The computer code in this program now shows how the code is written for Rayleigh damping. This for Rayleigh damping. You have to enter the degrees of freedom, you have to enter the mass matrix, in our case is the mass matrix. Similarly, one can enter the stiffness matrix, we have entered the stiffness matrix, then enter the damping ratio, we have taken 5%. Once you do that, then the Rayleigh constants are evaluated and then the damping matrix is evaluated and it is printed and checked for the third mode. So, the sample output looks like this my mass matrix, this my stiffness matrix, and these are my input frequencies which we already got 11.2721, 29.277 and 44.783 by computer program. The modal matrix what I get is what I gave you, this is my first mode, this is my second mode, this is my third mode, and the damping matrix is what I get here 3 by 3, which is exactly same. Let us say 6588, by hand I got 6543. Okay. So, that is what. So, it is going to be same, and check for the third mode damping ratio, I get 6.396, whereas we got third mode as 6.31. So, the computer program exactly solves the problem in the same style as we did by hand. A sample output is shown to you, and let us see the summary now. So, in this lecture friends, we learned how damping estimate is important in offshore structure, what is mass proportional and stiffness proportional damping, what is classical damping, what is the problem with the classical damping and why Rayleigh damping is appropriate to offshore structures, and how to solve C from Rayleigh damping. We also learned the computer method. We also have the access to the computer code. We solve the problem both by hand and by computer code, and we found the answers are agreement closely with them. I hope you will be able to program this in MATLAB and do couple of problems and realize how easy and convenient is Rayleigh damping for damping estimates in offshore structures. Thank you very much.